Good afternoon, everyone. In this presentation, I hope to describe to you how we can use Loadpull simulations to help with the optimum device selection for power amplifiers. Although I'm concentrating on GaN devices, the same process could be used for LDMOS. When faced with a module or system specification involving PAs, it's usually best to start with the final stage. Now, having said that, I get a number of customers who tell me that they've started at the back end, here at the input, because that's what the output of their synthesizer is, and they want 250 watts out, so they selected a 250 watt device, and they've already done the whole lineup based on a datasheet spec for that 250 watt device. So they just want me to do the last device. Everything else is sorted, and it doesn't work. So starting properly, we should start at the output device and then work backwards, because it's an awful lot easier to adjust the gain at low signal levels at the input than it is to start trying to find more gain from a 250 watt stage. But when we're trying to choose that device, we're faced with multiple options. How do we make the right choice? Well, we could stick with the tried and tested methods that we've always used, but then we're not going to have a competitive advantage if we're always using the same device. We could use data sheets, and a bit more on that in a minute, or we could trust the sales reps. Apologies to any in the audience for that cartoon. So having just said about data sheets and saying you shouldn't use them for choosing things, they're obviously our first port of call. But they give a very limited perspective on device behavior, as they'll often quantify performance either at a specific frequency or a particular number of frequencies that are very common and relevant. So you'll see a lot of data sheets say at 3.5 gigs or 2.7 gigs or something like that, but won't really give you the answer at yours. And they'll always have been very highly tuned at that one frequency. To get a proper handle on how suitable a device is for our application, we need to look at a simulation. Now, some old hands who've been around as long as I have will say, well, shove the device on a bench and test it. Well, if you've got 5 or 6 devices to choose, that's not a practical thing. I think that simulations is the way forward now, because the models have got, certainly from some manufacturers, have got very good. But for simulation to work, we need accurate models. So what is a good model? Well, realistic DCI-V curves, I would say, is a start. So does it simulate VDS breakdown? Can you include thermal resistance? And you need to be able to change it between pulsed and CW. Does the device take into account self-heating? Have you got access to the current generator plane? And if you have, the device also needs to be accurate at the harmonics for it to be of any use for you. And finally, how quickly does the model converge within the simulator? Because, again, to work sensibly for you, you need a model that's working relatively fast. So if we take, for example, choosing a device for a broadband amplifier stage, we could either do it single-ended with one device, or we could parallel up 2 devices if we're trying to cover 500 megahertz to 3 gigahertz and say do about 20 watts. So for the single-ended device, we're going to look at a 25 watt-ish device, and for the two parallel devices, we'll probably be looking around about the 12 watts. It's also useful to remember the relationship between RF power, the supply voltage, and the output impedance. What we're looking at, what would be ideal for us, is we had devices with 50 ohms output impedance. And we can see from these graphs, which I've plotted, which are the relationship between load resistance and output power at different supply voltages. If we're looking at about a 12 watt device, we want to be somewhere between 30 and 40 volts to get about 50 ohms output impedance. And for 25 watts, we're looking at around about 50 volts, and that'll give us a nice output impedance. And that's really an indicator of why device manufacturers are pushing the voltage up for higher power amplifiers. The output impedance is very low when you get up to the very high power levels, and if you can push the voltage up, then you can raise that output impedance. But that's not the only thing. You've got to remember the output capacitance, especially if you're talking about a broadband design. And that's a key parasitic that you have to take into account if you're going to try and match over a wide bandwidth. So in this example, I'm looking at 5 potential devices from Wolfspeed. We've got a choice of either using surface mount or flange packages. We can either use the around about the 12 or the 25 watt devices for our single-ended or balanced approach. We've got a choice of supply voltages of 28, 40 and 50 volts on this data sheet. And with all these options, it isn't easy at the face of it to come up with a definitive decision as to which is the best device to use. So putting together a simple spreadsheet, we can look at the temperature rise with those thermal resistances. And we can see immediately that one of the devices is hotter than the others. It's got a temperature rise of about 82 degrees centigrade. And also if we look at its ruggedness, it's only specified as 10 to 1 at 5 watts output. So it's the least rugged, it's getting the hottest, so we'll discount that one. But then if we look at the other ones, well, the one with the lowest temperature rise, that's a 25 watt device. It's got the lowest thermal resistance, so it'll probably give us the smallest circuit, but the output capacitance is 2.4 puff, whereas one of the others is 1.2 puff. So it's going to be more difficult to match that one over a broad band. So there's all these trade-offs we're trying to look at and trying to assess which one is going to be the best for our application, other than going to our project manager and saying, well, I've got a feeling. We want some concrete numbers and concrete answers. It's also worth remembering that for single-ended devices, there's going to be an awful lot of gain that we're going to have to lose somehow. And we can do that with feedback, but otherwise your single-ended design is going to end with a very poor match on the input at the low frequencies. Whereas if you go for a balanced design, all the power that's reflected back from the input of the device goes into the termination of the first hybrid. So there is another attraction to going for that type of topology. You may be relieved to hear that I'm not going to go through this whole process for every one of the devices on that list. What I want to do is show you the process that you can follow, and then when you've selected a device for your application, you should have a really good feel for it and be able to say concretely, this is the best device because, and have some measures. And also, by the time you've gone through this process, you'll have a very good feel for the performance of the device within the simulator. The basic evaluation circuit for the device is the source and load pull measurement setup. So we've got a tuner on the input which controls the source impedance. We've got a tuner on the output which controls the load impedance. And we can control up to 3 harmonics with the way that these tuners have been configured. A lot of research work has gone into harmonic source pull, but I don't really think it gives any significant benefit. There is some things you can do with limiting overdrive conditions and making the device a bit more rugged, but also source pull is quite a difficult one to try and achieve, so I'm not going to bother doing that. Now, as you can see from this setup, there's an awful lot of variables, and we could actually do a simulation with absolutely everything, and we'd make a massive amount of data, which we'd have to then sift through. And that's a bit like trying to find a needle in a haystack. It makes the simulation longer, and it makes any data post-processing difficult. And actually, it isn't a very scientific approach to just simulate absolutely everything and try and find the best combination. So what we need to do is start with applying a little bit of logic to the design. Another point that I think I should make out is that, remember, if you spend a lot of time developing actual matching circuits for a device, at an early stage, you can become emotionally invested into that approach. And your finance guys certainly will if you spent a lot of time designing something like that. So I think it's actually important to do this analysis without having designed any matching circuits. As importantly to rule out a device as it is to find a suitable device. Because if something isn't going to work, you want to know straight away and then cut it out of the list of applicants. Okay, so in the simulation, we first start by choosing the frequencies we want to test. And as a minimum, you want to do top, middle, and bottom. But if you're doing a very wideband design like 500 to 3000 megahertz, then you might want to put some intermediates in here. So I've done 6 frequencies in this case. We sweep the power, and you want to go the power over from so the device is in the linear region till it's about 5 dB compressed with a GaN device. We're going to sweep the gate bias voltage because that sets the IDQ, the quiescent current, and that determines which class you're operating in, whether you're going class A, class B, A, B, or class B. We control the source impedance that I mentioned and the load impedance. And in this case, I'm not going to bother swapping the drain voltage because I've set it for 28 volts for the maximum of this device, and I want to get as much power out of it as I can. So there's no point simulating something that I want to keep fixed anyway. To determine what bias voltages we need for the quiescent current, we create a DCIV simulation circuit. So this is the device here, and it was very quick and easy to connect up my power supply and run the simulation, much quicker than doing it in real life. And you can immediately see from these plots, the faded one is with the thermal resistance set to 0, and the bold one is with the thermal resistance value for the device from the datasheet. That we're actually getting self-heating in the device, and that we've got the breakdown at around about 150 volts. So we can be quite happy, at least in the DC perspective, that this device is modeling the sort of effects that we would expect to see. It's got the signs of a good model. To select the drain current, so I mentioned we're going to go from a class B, so down at the bottom here where marker 1 is. So we've got a little bit of current flowing through 50 milliamps, but it's not quite pinched off, but getting close to that. The top end where it's in class A, class A at half IDS. And then we're selecting another current in between so that we can get an idea of how the performance changes with these different classes of bias. Notice the red trace is the temperature monitor. On the Wolfspeed models, they actually give you access to a node which is proportional to the channel temperature. We don't expect it to run up at 300, getting up to 300 degrees C, because we're not going to bias it at 0 volts. But you have got this ability to monitor what the temperature is in the device. Okay, so how do we start off with our load pull? Where do we put our load pull circles? The blue grids here are the load impedance we're going to measure, and we start off at the center and we're going to scroll out. And so I've joined up the points on this grid so you can see how the measurement progresses as it goes further out. So where do we put our load pull circle when we start? Well, we use basic Cripps method of what's the output impedance of the device, which we get from the power and the voltage we're operating at. The capacitance is on the data sheet. And if we plot that with frequency, we get this green trace here. We want to actually not center the load pull contours on that, because if you're going to work in a higher efficiency mode, you're going to work at a higher resistance. So we offset the contours a little bit. But don't worry, if you set up your contours and it doesn't, and you find that your circles fall outside of this grid, you do a simulation and you recenter it. Okay. Oh, and also at the moment, we've set our second and third harmonic impedances. I've plotted those as well. We've just set those to 50 ohms for these simulations. So they're quite important to bear in mind for the future, that all the measurements that we're doing initially are with our harmonics terminated in a 50 ohm impedance. For the source, we've got our source pull grid, so that's these points here, and we're just basing that based on the conjugate of the input impedance of the small signal. So we can just look at the S parameters of the small signal of the device and say, okay, well that's the impedance we're going at, and we'll use those for starters. We'll go into it in a bit more detail later, but you need somewhere to start when you're doing your load pull simulations. Now, a quick point on the number of variables in a load pull simulation set. You've really got to keep an eye out, as the data file can quickly pile up. And it's especially relevant if you want to do any post-processing, as I've mentioned. Particularly at the start of a device evaluation, you might want to keep the data set smaller. For example, if we assume that we've got 6 frequencies, we've got 16 power steps, and we're going to vary over 3 gate voltages, that's already 288 simulations. If we then have 127 fundamental load impedances, and it sounds like a lot, but that's how many are on that grid, we're going to end up with over 35,000 simulations. If we then add in 7 source impedance points, we've now got over 250,000 simulations that we're going to do as part of this load pull. Now, it follows that if we halve that number of grid points, we halve the number of simulations. So 17,500, and then when we add in the source pool, we're just at about 123,000 simulations. Now just think about what 123,000 simulations means. If each simulation takes a second, that'll be 34 hours. Even if they take a tenth of a second, that's 3.5 hours. In fact, with these models, it takes more like a hundredth of a second. So it actually becomes a manageable time, and it's nice to have a simulation where you can go and make a cup of coffee, which I found I miss nowadays. But this will depend on the model, how good the model is and how good it is at converging. And it also will depend on how close to the edge of the Smith chart you get. I tend to find that if you're trying to make measurements at very low impedances, very high reflections, the model will take longer to converge, and that means your simulation time will go up. Okay, so the standard output from the simulation will look a bit like this. The red contours are of constant power, and the green are a constant PAE. We can see where the optimums are in the center with the hourglass symbols. And we can see how the performance changes with load impedance. And that's what we have to remember, is this is a shot of load impedance changing, of performance changing with load impedance. It's useful to remember that this is at a fixed input power, it's at a fixed bias and a fixed frequency. Now, if I refer back to the number of load points from that slide about data points, on this second graph, this is a graph that's made with half the load density. And can you spot the difference? Well, probably not, because you can't read the numbers as well as I can, but I can tell you that it's the second decimal point in peak power and 0.1% in peak efficiency. So certainly for the purposes of device comparison, we don't really gain anything from a high number of load measurement points. You have to get enough in there so you can get continuous contours, but you really don't have to go to town of stacking it full of measurement points. Now, a useful plot to include is the boundary where our targets overlap. So in this case, the red contour denotes where we're achieving both 33.5 dBm output power and a 55% PAE. Now we can step the frequency, and at this point I've actually also changed the source impedance, which you can see is now at gamma 7, whereas before it was at gamma 3. So I've gone up to 1.5 gigs, and then going up to 3 gigahertz. So I'm getting an idea of how the optimum or my target area changes both with frequency and also with the source gamma. And what I can then do is I can overlap at all the frequencies that I'm operating at. By changing the source gamma, I can get these contours to be around about the same area, about the same size for each frequency. So if I get it within any one of those circles at that frequency, I'm going to get 55% PAE and 43.5 dBm. And I can see that I've got an area in here where if I could match to that point, then I would achieve the performance at all the frequencies. And I've changed the source gamma in order to get those contours all to be about the same size. But again, we still need to look at what are the effects of other parameters. We're only seeing a slice, if you like, of how this performance is being affected. So another option we can do is we can actually look at the Loadpull contours when the device is 3 dB compressed. So we're plotting power contours of about 40, at 500 megahertz it's 43 and 44 dBm. At the other frequencies it's 44 and 45 dBm. That's these contours here. But this is with the input power automatically adjusted so that the device is 3 dB compressed. So we're looking at where the saturated peak powers are. And the saturated peak powers are different to the fixed input peak powers. And we can do that same thing and look at efficiency. So on this side we've got, on the left-hand side, we've got the power contours, and on the right-hand side we've got 75% PAE contours. And you can see there's a bit more dispersion when it comes to the PAE as opposed to the power. Now, if we select a specific source and load impedance, so we can go to our Loadpull contours and we can select a particular impedance by selecting that marker, and go to the source and select a particular impedance, and we select the frequency we want, and we can see the performance at that frequency. And here we can see that this device is already being compressed at the lowest power point. Now, of course, what we could do is we could have adjusted that input power and added a few more input powers until we got this into the back-off region, but that's going to increase the number of simulation steps. And if we repeat this now at 3 gigahertz, we've moved the fundamental marker over and we've moved the source marker over, and we're looking at the power plot. And here we can see at 3 gigahertz where we've got less gain, we're starting off in the linear region and we're going up to about 5 dB of compression, which is a good power sweep to have so we can evaluate the device properly. We can also replot on that graph, this time with all of the different, instead of using a fixed bias, gate bias, we're using all the 3 bias points that we've used. And now we can see the difference that you'll get from Class A, which is in the efficiency is this bottom one here, moving up to the Class B, which gives us the peak efficiency. And we can also see what it does to the gain. Interestingly, for this particular device, the flattest gain is in Class A. This is because when it's in small signal operation, the junction is at its hottest because it's got a fixed amount of bias current going through it. And then as we increase the drive power, it's getting more efficient. So instead of actually, the amount of dissipated power is staying the same, and the junction is staying the same temperature, so the gain stays relatively flat. But this won't be the same with every device. So you have to, this is a very important one to look at. Don't assume that you're going to get away with Class A and it'll be nice and linear. On a lot of GaN devices, if you run it in Class A, you'll see a constant power slope on the, slope on the gain even from low values as it's heating up. Now, on that earlier slide of the 500 megahertz, we were already saturating it. And you can see, just looking at the small signal of the device, down at the bottom end of the band, we're approaching 25 dBs of gain, whereas at the unmatched gain, the G max this is, and then whereas at the top end of the band, it's 15 dBs lower. So this is a problem that in broadband designs you've got. If you want to have a flat gain, you're limited by what's the best you can get at the top frequency, and then you've got gain to throw away at the bottom. And when you're talking about a power amplifier, throwing away gain isn't always as easy, because if your drive level is 2 watts maximum on your input, that means that's 2 watts of power you've got to somehow dissipate. So you've got to have components that are rated as handling that. As I said, if you're using a balanced design, it's not such an issue because you can reflect that back into the quad hybrid and then into the load of the quad hybrid and dissipate it there, and it's fairly easy to dissipate on that resistor. So if we look in at the source, we were just using a very simple source pull at the beginning. Now what I've done is we know where the optimum areas for our fundamental load, that's these blue crosses. But I've spread the source impedances over a much larger part of the Smith chart now. So we're going to look at what the effect is of varying that source impedance. And this is really to help us look at the matching circuit and how we can have a flat gain across the bandwidth. So what we've plotted here is the circles of constant gain, so 15 dBs of gain. So this brown contour is 15 dBs of gain at 2.5 gigahertz. So if we have our source impedance along here, and this is, remember, with our fundamental load confined to one of these points, which are sort of grayed out here, but correspond to the blue crosses, we can get 15 dBs of gain. And as we go down in frequency, we can get 15 dBs of gain if we put the source on there. But look, when we get down to 500 megahertz, we've got to put the source impedance way out here. And so if we designed an impedance matching circuit that went from this 0.8 up here and went through these contours, and at each frequency they matched up with a contour, so at gigahertz we were on this contour somewhere, we would get a flat gain. Unfortunately, that trajectory is really difficult to design in a real matching circuit. But because we plotted the contours, we might have noticed one other point. Down here at the bottom, all of these circles converge. So if we put our impedance down here at this point, and that is a much easier matching problem to deal with, we could get a flatter gain that way. So you can actually graphically visualize where is the optimum points. Okay, so now we want to take a look at the harmonic impedance effects. When we're looking at the fundamental, we knew roughly where to look. However, for the second, we don't know where we want to go. So we're looking for a steer as to where is the optimum place to take it. So we're covering the whole Smith chart. In a broadband amplifier, we can't affect the harmonic impedance at the lower frequencies. At 500 megahertz, the 6th harmonic is actually in band. So we have to concentrate on finding out what we can do at the top end. But we need to know what the effects are at the bottom end of the band. Because remember, when we did our initial measurement, we were using a 50 ohm impedance. So even so, it's, as I said, it's worth looking at what happens at the bottom of the band. So this is what's happening at 500 megahertz. And then what's happening at 3 gigahertz. And as you can see, we're getting a different effect at 3 gigahertz. And what's interesting is our optimum is over here, and our minimum performance, where we're actually degrading it. So we were originally tuning up here at 50 ohms. If we put our harmonic impedance down here, we're going to get less performance than we saw in 50 ohms. And if we plot the actual absolute maximums and minimums, one thing that's of interest is, this is the Class B on the left and Class A on the right. The maximums and minimums are actually very close together. And the analogy I like to use, it's like if you try and hit the maximums, it's like walking along the edge of the cliff. You might have the best view, but you're not far off falling over into disaster. So that's why we don't want to always aim for the absolute maximum. Again, I've plotted now, this is an interesting one because this is the difference between the Class B, which is on the left, and the Class A on the right. You can see that with the Class B, we can get, the optimums are about the same place, but we're getting much more spread of effect around the impedance chart. Whereas in Class A, we're getting very little effect in efficiency until we get right to the optimums. And then we're getting an even bigger effect, but you have to be able to ride in that optimum. And that means if you don't hit the optimum, it's going to fall off very, very quickly there. And that's because we're not producing very much harmonics with the Class A over most of the region. And then when you do, it can have a big effect, but you're going to be very, very sensitive to that harmonic level. I mentioned the current generator plane. So the device plane is where that's where we can impact on our device. We're looking at what we're doing at the actual leads, the connections to the device. But if you want to do any waveform engineering, you need to be looking at the inside of the device itself. And inside the device, we can look at the waveforms and current and voltage, and we can look at what the RF load line is doing. Now, to do that within Loadpull, what we need to do is normally we're conducting a set of measurements and we're measuring the A and B waves using these current and voltage meters on the drain of the device. But Wolfspeed and I believe the more recent Qorvo models now give you access to the current generator plane. And so what we need to do is conduct two identical load pulls, except with different pairs of measuring devices. And that way we can see both what's happening on the outside of the device and what's happening to the inside, to the current waveforms. And that way we can see not only what's happening in terms of performance and power, efficiency and power, but we can understand why we're getting more efficiency out. Because, for example, in this case, we're getting more efficiency because we're having less current when we have voltage, and we're also getting higher voltage peaks where the current is down low. And we can, as I mentioned, we can look at what the load line is looking like inside the device. Okay. There are two more simulations that I want to do, and I know I'm running short of time, so I'll keep it quick. But basically, this is taking it to looking at yield analysis. That's one problem that I've often been approached as, well, how do we do yield analysis on a device? Because which parameters do you vary in the device itself? Well, it's very difficult to know which parameters you can vary, but you can vary the load impedance. So now what I'm going to do is I'm going to vary the load impedance around a lot of points around this optimum, so somewhere within this circle we've determined, and we're going to step the harmonics. That we're going to keep them near the center of this and then move out towards the edge, which is a more likely response that we're going to get with a matching circuit. So this is with looking at the effects of the various load impedances at 500 megahertz. So these are all the fundamental load variations, and this is at 500 megahertz and 3 gigahertz, but with the harmonic impedance, this gamma L2 stepped to where it's optimum. So we're peaking up the performance a little bit at 3 gigahertz, but we're not doing anything at 500 megahertz. So you can see the gammas have changed there. And now this is doing it including source variation as well. So the grey are all the impedance points. The blue just happens to be the ones I've chosen as typical. But now you can get an idea of spread that you're going to get out of the device when you're varying all the source impedances and the load impedances. And you could even start adding things like, well, what about if the gate voltage varies a little bit because equivalent to the drain current being varied a little bit. So you could add, you can get a sort of a tolerance analysis out of it. So coming to the end of the process now, we've now got a measure of the dispersion of the optimums for the key parameters with frequency. We've got an idea of the size of the target area that we're going to aim at. We know the sort of impedances we're looking at, and that's so important. And we know what sort of gain, a realistic gain we're going to get across the band, which is important to specify in the driver device. Remember that we've been doing load pulls, so we haven't taken into account at this stage any of the device losses. It's any of the matching circuit losses. You need to allow for those. But very importantly, we've done a lot of simulations on the device. We've got a good feel for it. We know how realistic it is as a device. So we're going to have a lot more confidence now in specifying it. And we might have, by this stage, have ruled out a device and said, look, this one isn't, we can't go forward with this one. And it's particularly if you start with the device that you feel most confident in, when you're doing the comparisons of the others, if you see they're not working out as well, don't have to go through the whole process. You can say, I'm stopping with this one because it's unstable, it doesn't converge, because the input impedance is poor. Okay. I think that just about covers everything I wanted to say, so thank you. Lunch has silenced everyone.
Which device did you choose?
Actually, although I did all the, on that particular one, although all that analysis was on the 25 watt, we went for two 10 watts in parallel because of that input matching and the ease of reflecting the power into the quad hybrids. But we were lucky that 500 megs to 3 gigs, there are quad hybrids available. You don't always have that.
Great question.
Do you find that you get a different, almost like confidence level with different models from different manufacturers? I mean, I noticed there you were comparing lots of Cree devices.
Yeah.
But let's say you've got a Cree device, a Hittite device, a Macon. You know, do you find that you trust Cree but you don't trust Hittite, let's say? Not mentioned, you know.
I certainly do trust Cree because I've been working a lot with them, and the more recent Qorvo models are much, now that they've gone to monolithics to making them. There's an awful lot of people who are making spot frequency type models, and for telecoms, well, you can understand that, but most of my work tends to be, well, can you do a frequency band that isn't quite right? So then you need a really good compact model. But I know the guys up at Iconic have got a paper coming up at ARMS about modelling, and it's good to see that some of the other device manufacturers are appreciating that if you want us to use them, you have to give us a good model.
Okay, thank you very much, Dominic.